We are living in a modern world where electricity has become an indispensable source of life. From the bright lights that keep cities awake, to the giant industrial machines running day and night. From the tiny devices in our hands, to the complex global systems, everything silently depends on electricity. So, what is electric current? In this video, I will explain what current really is, and its basic properties. Imagine this simple experiment. Take a small motor from a toy car, connect it to a battery, and the motor starts spinning. You may think it is normal, but ask yourself, how does the energy from the battery reach the motor? Think of a hydraulic system, where oil is pumped through pipes to a piston, creating force and moving parts. It is easy to picture energy transfer as the flow of oil. In an electrical system, the battery is the source, and the wires connect to the motor. Energy seems to flow from the battery, through the wire, to the motor, just like oil flowing through pipes. But wait, if you cut the wire and look inside, you do not see any flow of energy. So, where does the energy really go? Let us zoom into the wire until we can see each atom inside. At that scale, the wire is no longer a smooth strand of metal, but a vast lattice made of billions upon billions of copper atoms packed closely together. Each copper atom has a nucleus at the center, surrounded by electrons moving in orbits. The special thing about metals is that some outer electrons are not tightly bound. They can move freely from one atom to another. These free electrons are the carriers that transport electrical energy. So, how do electrons move? When a battery is connected, the positive terminal attracts electrons, and the negative terminal pushes them away. Electrons start moving from the negative side toward the positive side. But do not imagine electrons racing from one end to the other at the speed of light. Most people think that way, because in reality, when we flip a switch, the light turns on instantly. In fact, each electron only moves a tiny distance, and it does so very slowly. You can imagine it like Newton's cradle, the desk toy with metal balls. When you lift one ball on one side and release it, the ball on the opposite side moves instantly, even though the balls in the middle barely move. Electric current works the same way. Each electron moves a little, but the effect is transmitted instantly across the wire. Because billions of electrons move at the same time, the electric current is established almost instantly across the entire circuit. That is why when you flip the switch, the light turns on immediately without waiting for electrons to travel all the way from the battery to the bulb. In this way, electric current is simply the directed movement of free electrons in the conductor, driven by the pushing and pulling force of the power source. But here is a question. If electrons move from negative to positive, why were we taught that current flows from positive to negative? This is the difference between conventional current and the actual movement of electrons. At first, scientists did not know electrons existed. They assumed current was something positive, so they defined it as moving from positive to negative. Later, when electrons were discovered, people realized electrons move from negative to positive. But the old convention remained, and is still used today. Let us now explore the basic quantities of electric current. The first one is current intensity. In English, it is called current intensity. It is symbolized by the letters I. Its unit is ampere. You can imagine electric current like the flow of water in a kettle. When water flows through a point in the kettle, we can measure how much water passes that point within a certain period of time. In a similar way, current intensity tells us how many charges pass a point on the conductor in 1 second. If in a wire, 6.24 2 times 10 to the power of 18 electrons move across one point in the circuit within 1 second, then that corresponds to a current of 1 ampere. Because the number 6.24 2 times 10 to the power of 18 is extremely large, to make calculation easier, we use a unit called coulomb. 1 coulomb is equal to 6.24 2 times 10 to the power of 18 electrons. After understanding current intensity, next, we will learn about another important quantity. That is the electric potential difference, or simply voltage. To make it easier to imagine, let us think about the pressure of water. When the water level in a tank is low, water flows out of the faucet slowly. But if the water level in the tank is higher, the water flows out stronger and faster. This happens because a higher water column creates greater pressure, which pushes the water out with more force. That water pressure is measured with a pressure gauge. Similarly, in an electric circuit, voltage is like the pressure that makes electrons move inside the conductor. The greater the voltage, the stronger the current flows through the circuit. For example, if we use a 1.5 volt battery to power a motor, the motor will spin slowly. But if we connect two 1.5 volt batteries in series, we will have a total voltage of 3 volts. Supplying this 3 volts to the motor will make it spin much faster. This shows that increasing the voltage will increase the amount of energy delivered in the circuit. One invention has changed the whole world, pushing back the darkness of night. That is the incandescent light bulb. Although it is such a great invention, its working principle is actually very simple. We know that electric current is the movement of electrons inside a conductor. But inside a conductor, the path is not a smooth tunnel. As electrons move, they constantly collide with atomic nuclei fixed in the crystal lattice. These collisions make the conductor heat up because part of the electron's energy is converted into heat. Depending on the type of material, this resistance level will be different. For example, in copper wire, electrons encounter less resistance, so less heat is generated. But with a material like tungsten, the resistance to electrons is much higher. When the current is strong enough, tungsten can be heated close to its melting point, and it emits light. This phenomenon created the very first glow of the incandescent bulb. In short, resistance is the property of a material that opposes the flow of electrons. It turns part of electrical energy into heat or light, and the higher the resistance, the harder the current can flow. So, we have learned what electric current is, how electrons move, and the basic concepts of current, voltage, and resistance. If you find this video useful, please like, share, and subscribe to support the channel and not miss the next lessons.